Okay, let's take a look at week 3 ACT Prep science questions. So this first one should look very familiar because we've seen it before. It's all the same information. It's the photosynthesis one that's talking about C3 and C4 plants and the rate at which they basically convert carbon dioxide into sugar and oxygen in different lights or temperatures. The question, however, is which kind of plant contributes more to the global problem of removing carbon dioxide from the air? Pardon me, I have a little cold this week. So, if you're just thinking about that, which one removes more carbon dioxide from the air, you can look at these and say, well, I think that it's C3. No, I think C4 has more of it overall. And you can do that up and down, and you might even say both. And that's the first three answers, but they're all wrong. And the reason they're all wrong is because it wants to know which contributes more to the global problem. We don't know how many of these plants there are. What if there's only one C3 plant and billions of the C4? Then the C4 is going to contribute more regardless of the rate at which they're doing. They're getting rid of carbon dioxide. So we don't have enough information, and that's what Jay says. There's not enough information, and that is, in fact, the answer. Now, number 2, it's still that same thing, all the same stuff over here. This time it wants to know the graphs do not give us any information about, so we need to figure out what we can't learn from it. The temperature sensitivity of C3 plants. The temper sensitivity. Well, here's temperature. There's C3 plants. So there is some sensitivity to it. Doesn't look like it really does react to it, but that still gives us that information. Then this one, the minimum light intensity for photosynthesis in both kinds of plants. Well, if I go to light intensity and I see that they both dead end here on 0 rate, then that has to be my minimum. It's the lowest I can go. It's not going to start doing the opposite of what a plant does. It's not going to start doing what we do and taking in oxygen and producing carbon dioxide. And so 0 is your minimum. We know that. The limit on the effective light intensity for C4 plants. Well, if you notice, this is the C4, this is light intensity. It pretty much comes to a nice straight line. That usually means that it's kind of limited. It's bottomed out. It's limited. So we have that information. And then this last one, the relative importance of light intensity and temperature in determining the rate of photosynthesis. Well, we're told about the rate of photosynthesis, and we're told about it with light sensitivity and temperature. The key word here is relative importance. Relative. Relative to each other, we have no idea, because the rate isn't marked in a certain scale. What if our scale for light intensity was in like 10s, 20s, 30s, 40s, all the way up to 100? But then our scale of the rate scale for the temperature was in 0.1, 0.2, 0.3, all the way up to just 1. You can't compare these then. So since we don't have that scale, there's no way to compare. We can't do the relative importance to one another. And so that means it's J. J is our correct answer. Oh, we've seen number 3 before as well. So this is the fun little lab where they're growing different bacterias, a Y and an R. They're putting it in different mediums, glucose, basically a sugar, amino acid, a protein, and then both of them together. Let's see what it's asking this week. What statement describes the nutritional requirements of the R bacteria? Well, this is the experiment that we're doing on the R bacteria. And so let's take a look. They require both glucose and amino acids. Well, when it had glucose and amino acids, it did grow very well. But it also grew very well with just glucose. So it didn't need both of them. So I'd say no, not that one. They can live on glucose alone. Well, it did. So I'm guessing that one is true. But let's take a look at the rest of them as well. Amino acids retard their growth. Nah, they still grew a little bit in amino acids. They cannot live without glucose. Again, they grew some in just amino acids. That was without glucose. So it looks like B is the only one that makes sense. They can live on glucose alone because they did very well when they just had glucose. So our answer is B. Okay, number 4. We've seen it before as well. It's the experiment with the different halogens. They're putting a halogen solution into a salt solution containing the different types of halogen. So in the first one, they put chlorine in a potassium chlorine, potassium bromide, potassium iodide, and water. The second experiment, they put iodine, and they put it in all four of those. And then they had bromine, and they put it in all four of those. And they get what color the solution turns, right? And we know whatever color it turns is whichever one was knocked out of the solution. So what it's asking this time is, why was the halogen solution tested in water in each experiment? Well, that's a good question, because it's not going to knock anything out of water, we hope. But what water is it's the control. And the control basically shows that nothing else is going on with it. That it's not randomly turning a color because of some other compound in the solutions, right? It shows that just that solution or just that alone is going to turn that color. And so if you notice, the chlorine was put in water, it turned green. Chlorine is green. Iodine was put in water, it turned dark brown. Iodine, it shows up as dark brown. And then bromine put in water, light brown. It is light brown. Also notice that that's actually part of the experiment, that when they're dissolved in water, they have a distinctive color, right? And so that probably means that these salts, it's not just a hard crystal salt. It's probably a salt solution, which is probably made with water, the solvent. Water is one of the greatest solvents we have. So they're already being added in something that has water in it, right? And so we want to see what just that one looks like when it's in water. And so we're observing the original color. That's what we actually get to do when we put it in water, to make certain that the outcome is not just a reaction with water. Well, that reaction is really what we are looking for. We're looking for that color in water. And so we're looking for it to turn that. We want to see that reaction, so it wouldn't be that one. To test the purity of the halogen solution, that's not really how we would test it. You would test it with other reactivity type things. You don't want to test it just in water. To make sure there are no contaminants in the water. Well, we're not testing the water, so there's no reason that we would do that anyway. And the solutions wouldn't be made with the water that would have contaminants in it to begin with. It would be made with a very pure water that they use in lab scenarios anyway. I can't think of the term right now, but it's just water. It has nothing else in it. Distilled water. Okay, so that means they really are just looking to make sure that it does what it's supposed to do, and that that halogen turns that color when it goes into the water. And so they're observing the original color. It's the control of the entire experiment. So A, to observe the original color. Okay, so the last one we have here is we're looking at these two guys that are talking about putting manganese in fuel in order to have increase the gas mileage. And so we've seen these arguments before. I hope you read them again so you had a good idea of what they were talking about. This scientist, as I recall, was for it. This one was against it. This one says that we metabolize all of that through our blood, through our liver, so we're okay with it. This guy says, oh no, it doesn't go through the liver, it goes directly to the brain when we inhale it. This guy says, look, it's not the same as when we did this with lead. This guy says, don't forget, we did this with lead and it was terrible. And so they're just back and forth. They're completely contradicting arguments. So it says here, past experience with leaded gasoline centered into this dispute because. Well, we just said scientist 1 said it's not the same as when we put lead. It's not deadly like that was. Scientist 2 says, oh yeah, this is probably going to turn out to be just as deadly, but we had to study it too, so let's not make the same mistake. So the first one here, it says the two scientists do not agree that lead is harmful. No, they both agree that lead's harmful. They both are saying, yeah, that one was terrible. But this isn't the same thing as what this guy's saying, and this guy's saying it might be. The psychological effects of manganese are similar to those of lead. It doesn't say anything about psychological. That's physiological. Sorry. Physiological. No, and they don't say anything about physiological either. Scientist 1 feels that the experiences with leaded gasoline have clouded the whole issue. Well, yeah, he says the only reason we're worried about this is because lead was such a big deal. So that one works. And then lead and manganese both travel to the brain through, well, that doesn't even have to do with lead, really. So, no, not J. Leaving us with H. Only reasonable one. All right. And that is all of them. I hope you have enjoyed this or just learned what you need to learn. Either way, we're good. Good luck.